Good afternoon. My name is Nyazi Faizo, and I want to share with you my presentation for the review paper. I'm reviewing a paper titled A Novel Lower Extremity Non-Contact Injury Risk Prediction Model based on Multimodal Fusion and Interpretable Machine Learning. I'll go straight forward to the computational problem. And in this paper, we are trying to solve or look at the problem of injuries, and we're trying to predict the injury risk patterns using a multi-modal fusion model and machine learning algorithms. And the data, so the computational problem here is that the data that has been used in these studies is primarily multi-source and multimodal, resulting in the models not fully utilizing the information that is in the data to review the specific risk patterns. Because, multimodal, when we say multimodal strategies or fusion, we are talking about multiple forms of channels, so how to convey a message. So in this case, we are talking about the training load, the perceived well-being status, the psychological responses, the physical performance, and the lower extremity, non-contact injury registration, and everything. Another problem is that the current methods face challenges like complexity and uneven distribution of the injury samples. And also the cost of the misused diagnosis was much higher than the injury misdiagnosis, and using the accuracy alone as a model evaluation that, of course, was not appropriate. So what solution did these people come with? These people came with a solution of the LENCI, what's this? The study proposed a lower extremity non-contact injury risk prediction model that we're going to see through this lecture. And it's based on multimodal fusion and machine learning algorithms, that has already said, to handle multi-source data, to transfer data and predict also the injury risks. And in the application domain, we're talking about the parameters that we're going to be working within. Here we're going to, let's say, for example, it's a data set, and it's going to be having 16 young female athletes on a basketball team. And this study has been carried for like 20 weeks. Yeah, from November 2020 to April 2021. Yeah, so those are the modality. We can call the modality or the things we're going to consider: training load, perceived well-being status, psychological responses, physical performance, player injuries. Yes, and it was also approved by the Fijian Provincial Basketball and Volleyball Center. Now, the models that were used, the models as we were talked about it, which is the multimodal fusion model, and this model combines two algorithms. Yes, the XGBoost algorithm and the random forest algorithm. What do we use the XGBoost algorithm for? We use it for unimodal submodels. What do I mean? I mean constructing predictive models using a single modality. You get? So in this paper, it could mean constructing models separately for each modality or for each type of data. For example, training load. So the random forest for constructing multimodal fusion model is also another algorithm, because it's aiming for generality, interpretability, and ease of implementation to aid in injury risk prediction and prevention. Yes, the monitoring methods, as we see, we use Borg 10 RPEF scale for the training load, a well-being questionnaire for the perceived well-being status, physical performance tests and analysis for psychological responses, injury registration. For every monitoring method that was used, it had a corresponding result. And as you can see, the above word, those are the methods that were used, and also the data that was collected. The approaches that we used in this study, mainly we've found two approaches that were used. The study employed the time sliding window technique. Yeah, it employed the time sliding technique to pre-process the data set. And this accounts for the accumulation and decay of players' response to training load and perceived well-being. And also something I'd like to add on that is that the data, another approach that we use is stratified cross-validation and reviewing historical data to prevent overfitting, of course, which Mr. has been talking about it for some time now. But another thing about the sliding window technique is that it's involved in creating an aggregation sliding window, so enabling statistical calculations on the variables within the aggregation window. Yes. So model construction. As you can see here, we have 4 modalities, which is the training load, the perceived well-being feature, the psychological response feature, and then the physical performance feature. Now, these are from dividing the monitoring indices. Yeah. Now, using LENCI as a dependent variable in the next week, the multimodal fusion model construction process involved initially, we begin by constructing submodels for each modality using dataset A. The decision level fusion determines the model parameters of the fusion model, or what we can call the W fusion model, as you can see on this diagram. The W fusion models. Yes, subsequently, the submodels for training, the training load and perceived well-being states were constructed using dataset B and integrated into final injury risk prediction models. As you can see here, this is what I mean. They were trained and then they were integrated so that to get the injury risk prediction model named D. Here. Yeah, so, and we already talked about the algorithms that were used, which is SG Boost, which is chosen because of its classification ability and its training speed, and also the random forest RF for constructing the multimodal fusion model. Yeah. We can go on to the next slide, which is model validation. How was this model validated? The study employed a 10-field stratified cross-validation strategy to evaluate the proposed model's performance. And the original data set was randomly divided into 10 data sets. And each is used as a validation set. In turn, while the remaining subsets, they serve as a training load. The average performance over the 10 iterations is calculated as the overall model performance. Yeah, I think this makes sense. And the 2 experiments that were conducted, we compared it with the unimodal submodels and also with different fusion schemes. Yes, the model evaluation. Model evaluation, the study, how can I say this? Yeah, the study evaluated the model using precision, recall F2 score as indices for model performance, of course, and they're calculated with true positives, false positive, true negative, false negative, and then the decision curve analysis was also employed to evaluate the model's clinical utility, determining the net benefits of intervention for predicted positive and negative exposures based on probability thresholds. And that's how it looks like. Our decision curve analysis, as we have said, is simply to evaluate the model's clinical utility. So determining the net benefits here, net benefits on this side, and then the threshold probability you get of intervention. So you get things like this, the minimal. Another thing that I want to talk about is the model performance evaluation of the fusion models. What do I mean? The prediction models were constructed using this table as independent variables, and then the LENCI in the coming week who acted as the dependent variables. So dataset A with training week as the acquisition frequency, and then dataset B with the training day as the acquisition frequency were generated, and output variable imbalance ratios in datasets A and B. Yeah. Then the W fusion model, as you can see here, these ones, the W fusion models, because they're constructed based on the dataset A, and they are used to predict dataset B. So the submodels D are trained using dataset B's perceived well-being and training load data and shows significantly better performance than dataset A. And then this is our confusion matrix for the W fusion model and the D fusion model, as I've been explaining. And then we have table 5 that is showing the performance evaluation results of the fusion and the integration schemes in dataset A. So after the fusion, I've been talking about now the results that we get from the different models, as you can see, SG Boost, DV fusion model. Yeah, I saw there. Other multimodal fusion strategies that I've been talking about. Like data level fusion, and we have we have the other fusion strategies we have is data level fusion and intermediate level fusion. The decision level strategy that is employed in our model was deemed effective than these two. You get why? Because it has this ability to isolate errors from different submodels, thus preventing the further accumulation and facilitating informed decision making. You get, but everything is an advantage as a disadvantage, of law of opposites, and the risks of this LENCI, which is the lower extremity non-contact injury risk prediction model, is that differentiating between the risks. That's the first thing I'm going to talk about. The first risk is differentiating risk patterns. For minimal LENCI risk, perceived wellness status and physical performance contribute significantly, as indicated by increased weights of submodels in the fusion model. Then another problem is complex interactions. Complex interactions. What do I mean? The different risk patterns are depending on various factors such as sport types, injury types, severity. So you cannot easily predict like what sport, and it's a limitation, it's a risk. The impact on well-being and performance. Athletes show worse perceived well-being and physical performance during the minimal LENCI risk, possibly due to prolonged overtraining. People can overtrain, and so the impact on well-being and performance will be affected because it won't be good. Advantages of this model, the ones I can talk about are the model demonstrated high precision and recall rates for predicting non-injuries, minimal less risk, and mild. DCA confirmed the practicability of the model in training practice and can also obtain more accurate results in predicting severity in the players. Limitations: the model wasn't validated for external validity. Injuries are unpredictable. The amount of data that is used in the study was small. The study doesn't focus on specific injury types. I've already mentioned in the risks. So conclusion is that Conclusion: the study introduces a novel risk prediction model for lower extremity and contact injuries and employing a multimodal fusion approach combined with machine learning algorithms. It demonstrates the effectiveness in predicting injury risks of varying severities among adolescent female basketball players. So the comparative analysis with both the submodel and the traditional data integration schemes that confirms the validity of the proposed methods. And despite the promising results, it's important to acknowledge certain limitations of the study because, of course, it's limited, and the future endeavors will focus on expanding the dimensions of data collection and incorporating more comprehensive indices. Thank you. And before I go, the references, there are very many references to this, of course.